Okay guys, so welcome back. Today we are going to be looking at using chords. So a few theorems that we have to go over before we can solve these. The first one is the congruent corresponding chords theorem. This basically states that in the same circle or in congruent circles, two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if you look at this diagram here, we can see that chord AB and chord DC are congruent, therefore their corresponding arcs, so arc AB and arc DC, are also going to be congruent. So, in other words, congruent chords create congruent arcs, and congruent arcs create congruent chords. All right, the next theorem we're going to be talking about is the perpendicular chord bisector theorem. So this states that if a diameter of a chord is perpendicular to a chord, then the diameter bisects the chord and its arc. All right? So in other words, if a diameter and a chord intersect, then the chord gets cut in half, so it gets halved. All right. So then in this case, if we look at this diagram, if EG is the diameter of this circle, it's going to bisect the chord FD, and it's also going to be perpendicular. So it's going to be a perpendicular bisector of the chord DF, meaning DH and HF are going to be congruent. So likewise, the perpendicular chord bisector converse states that if one chord of a circle is a perpendicular bisector of another chord, then the first chord has to be the diameter. So in other words, if one chord is the perpendicular bisector of another chord, then it is a diameter. There is one other theorem that I want to talk about that wasn't stated in the notes, so I actually want you guys to include this. This is going to be called the equidistant chords theorem. All right, so this basically states that in the same circle, or two congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so in other words, if you have a circle, all right, and let's say that we have chord AB and chord CD, and we have, let's call this circle E. So basically, we know that these two chords are congruent if they're equidistant from the center, meaning if we were to draw perpendicular lines, we know that that's going to be the shortest distance from a point to a line. You guys should know this, right? So if the distance between the point and the line and the chord are congruent, then that means that these two chords must be congruent. So AB is congruent to CD if and only if EF is equal to, if EF is congruent to EG. Okay, and this would be F this would be, this would be G. Okay, so let's look at example 1. If we look at example 1, we have, it says in the diagram, circle P is congruent to circle Q, and FG is congruent to JK. And measure of arc JK is 80 degrees. We want to find the measure of arc FG. All right, so we know that these two circles are congruent, right? So if we know that the two circles are congruent, and we know that both chords rather, are congruent, then that means that both of the arcs, the corresponding arcs of each of the chords have to also be congruent. So by the congruent corresponding chords theorem, because JK is congruent to GF, the corresponding, spelled that wrong. Minor arcs FG is congruent to JK. Therefore, if the two chords are congruent, if the arc JK is 80 degrees, then arc GF must also be 80 degrees. All right, so looking at example 2, we have a diagram of a circle whose diameter is perpendicular to a chord. Now, we know that if a diameter is perpendicular to a chord, then by the perpendicular chord bisector theorem, then we know that NH is going to have to be congruent to NK, because we know that they're not only is it perpendicular, but it is a perpendicular bisector. So if NK is 7, then HK must be 14. The reason we know this is because if NK is 7, then NH is also 7, so then the entire distance would be 14. Another thing that the perpendicular chord bisector theorem states is that not only does it bisect the chord, but it also bisects the corresponding arcs, right? So if it bisects the corresponding arcs, then we know that these two arcs are going to be congruent. So I could set 11x equal to 70 plus x and just solve for x and then plug it back in, right? So if I solve for x, I'm going to subtract x on both sides. I end up with 10x equals 70, and therefore x equals 70. Now, to find measure of HK, so arc HK, I'm just going to plug that back into both of those, or I can plug it into one of them and just double it since they are the same. I'm going to plug it into 11, so 11x, so I'll plug in 70 for x, and I end up getting 77. Now, since I know that both of these are going to equal 77, since they have the same measurements, then I'm just going to double it. So I'm going to do 77 times 2, and that gives me 154 degrees. Okay, looking at the next example, it says in the diagram, QR equals ST, which equals 16. SU equals 2x, and CV equals 5x minus 9. We're asked to find the radius of circle C. All right, so just looking at this diagram, we can see that the diameter here is WX, right? So now if the diameter is WX, you can see here that it forms a perpendicular line with chord QR. Now, we know from the perpendicular chords bisector theorem that if the diameter is perpendicular to a chord, then it also bisects the chord and it bisects the arcs, right? So then we know that these two are going to be congruent. Now it tells us that QR equals ST, and they're both 16. So if this whole chord is 16, then that means each of these is going to be 8 degrees, right? Or 8 units. They also tell us that CU is 2x, and they tell us that CV is 5x minus 9. We're asked to find the radius. All right, so the very first thing we want to do here is we want to set 2x equal to 5x minus 9. Now, the reason we can do this is because we know that they are equidistant, right? So from the equidistance chords theorem, we know that these are equidistant, meaning that they are going to have the same exact measurements. So I'm going to set them equal to each other, and I'm just going to solve for x. So I'm going to subtract 2x on both sides. So then and I'm going to add 9 on both sides. So these cancel. I'm left with 3x equals 9, and then x equals 3. All right, so now to find those distances, I'm just going to plug it back into one of those expressions. Now, it doesn't matter which one because we know that they're the same, right? So obviously, I'm going to choose the easier one, which in this case would be 2x. So I'm just going to plug it into 2x. I'm going to do 2 times 3. That gives me 6. So then I know that this is 6, and I know that this is 6, right? Okay, so now they are asking me to find the radius. Now, I can draw a radius anywhere from this circle, from the center of the circle to the end of the circle, or to the actual circle, right? So, if I drew a radius from point C to point Q, then, as you can see, I have formed a right triangle, right? And I now know 2 sides of my right triangle, so I can just find the third side using Pythagorean theorem, right? So I already know that this side length is 6, right? So I'm just going to do 6 squared plus 8 squared equals r squared, right? Which is, in this case, the radius. And then I'm just going to solve for r. Over here, I get 64 plus 36 equals r squared. That gives me 100 equals r squared. And I'm going to take the square root of both sides, and I get r equals 10. So then my radius here would be 10.